Okay, so in this video, in this section, we want to talk about double integrals and volume. And so I kind of, I already gave it away. I already spoiled it for you in the last video, what this double integral is. It's the volume underneath the surface, right? So if we were to graph the surface, right, and this could be a plane, of course, or it could be any curved surface, right, sitting above some region of the xy plane. So here's the xy plane. Right? So this could be the x-axis, this could be the y-axis. Right? And let's suppose the region is this region here, right? I'll call this R. So in other words, we're only looking above that region. And we just barely hit it up here, right? So this might end up being some sort of curved surface here. Oops. Right. And the region between that surface, right, and the xy plane gives us some volume. And so if we just take a little column here, like just pick a little tiny square or rectangle here, and just call it dA, or delta A maybe, because it's a finite area. And we go up to the surface here. And if we can calculate the volume of this rectangular column here, pretend it's straight, right? That gives you just essentially, approximately, the volume of a little box here, right? We know how to calculate those. Again, forgive the sloppiness, right? So the idea is just to take a bunch of these and then just add up all those volumes. Right? So this is going to be the limit as the norm of the partitions approach 0 of the sum, say I goes from 1 to n, of f of xi yi times delta a I, so this is the ith square or rectangle. Right? And when you take that limit, you get the exact volume. Right? So this is effectively another Riemann sum that you probably dread from your Calc 1 days. Right? And in Calc 1, I don't make a big deal out of this. If you love to go into the details here, take a course in real analysis, and you will spend a lot of time analyzing, no pun intended, situations like this where you want to, evaluate an integral as a Riemann sum. It's just one way to define an integral is using the Riemann sums here. So, all right, so we really don't need to know any of that here. Just the basic idea that this double integral here, this is called a double integral, and it represents the volume of this region. This entire region underneath the surface, but above the xy plane, above the region R here. Okay, it's sloppy enough, but it should give you the right idea. I mean, again, there's better pictures in the book, so that's fine. And these are some of the properties of these double integrals. And most of these, I think, are pretty obvious. Again, we're not going to prove them. Again, take an analysis course if you want to prove them. But in terms of just what they are, the first rule here is really just the constant times the function rule. You have a constant times a function, right? That constant can come outside the integral. Right? Same as Calc 1. Right? In Calc 1, you had a constant times a function with respect to x. Of course, you can take the constant outside. We do that all the time, right? You also have the sum rule, right? You remember the sum rule for single variable integrals? It also works for double integrals as well. So I can split this up as the integral of f plus the integral of g. Right, no problem there at all. The third maybe needs a little bit of explaining. So if the function f of xy is greater than or equal to 0, then the double integral of that function also has to be greater than or equal to 0. Well, that just coincides with what we were talking about earlier, right? If you have some region, it could be a rectangular region or a square region, and you have your surface sitting above it, that's the surface, right? Z equals f of xy. Then, right, it represents the volume of that region above the region R, the solid region below that, but above the square, above the rectangle. So volume is positive, right? Volume is positive. So that's all this is saying. Right. It's no different than in Calc 1, where you had a positive function or a non-negative function, and then the definite integral had to be non-negative as well. And again, that's just when the function is above the x-axis, this area is a positive area, right? Right. Now, in Calc 2, you did talk about what happens when your function dips below the x-axis, right? Then the definite integral could very well be a negative number. So if you want to talk about the area, then you better take the absolute value, right? Make it positive. So the area is not negative, but the definite integral could be negative, right? And so that same thing could happen here. If this is the xy plane, let's say, but your surface is below that plane, your surface is sitting underneath of it, right? Underneath it, then this volume here will be positive. However, the double integral could very well be a negative number in that case. Okay, so that's number 3. Number 4 is very much related. All it says is that when one function is bigger than the other, right, if f is bigger than g, then so are the double integrals. Yeah, definite integrals, double integrals, right? Double integral, right? And that just means if one surface is above another surface, then the volume below it obviously will be bigger, right? Yeah, should be obvious in that respect, right? And then number 5. So this is an important one. Maybe I shouldn't use red for that. Number 5. This just has to do with the single function f, right? So here's your surface again. Z is a function of x and y, sitting above the xy plane. Right. But now, suppose that you have a region here, and suppose you just want to consider, well, like the first example we had in the previous video. Like let's say instead of a rectangle, we have a rectangle with a semi-disk here, semicircle. Okay. So if you want to calculate the definite integral above both parts of this, right, if this is the entire region R here, right, right, this is nothing new. We divided this into 2 regions, R1 and R2, and then just added up the the double integrals, or the iterated integrals in the last video. Okay, so yeah, you can do that, right? In Calc 1, if you have one function here and then another function here, say from a to b and then from b to c, the definite integral from a to c, well, you can divide it going from a to b first and then going from b to c. So that's the analog to this property here, property 5. Okay, so yeah, it's just a bunch of properties. Most of them I think are fairly intuitive. We are going to use 5 probably a lot more than the others, but the others are important as well. Okay, so now comes the most important question. We have these double integrals, and for the moment, these are kind of abstract, right? These double integrals, all we know about them is that they represent the volume underneath some surface, right? So if we have a paraboloid, and that's my z as a function of x and y, and I have the xy plane below it, and you have certain region here, right? Then the volume underneath the surface, right? If you want to calculate that volume, you calculate the double integral, right? And that tells you what this is. This is the volume. So it's a number. You end up with a number that represents the volume. Right. So this is the volume of the solid region below the surface. Oops. Or yeah, okay. I should say between the solid region between the region R of the xy plane and the surface, right, f of xy, sitting above that region R. Okay. Right. So, yeah, kind of an abstract idea here. I mean, the volume is not abstract, but just this notion of the double integral, which, you know, the definition of that is abstract, right? It was defined this way, which I never really explained, and I'm hoping I don't have to, because, you know, that would probably be a more advanced course, either an advanced calculus might explain this better, or real analysis. So if you're interested in this, great. Take a course in advanced calculus or real analysis. But we're not going to do that here, right? We need a more practical way to calculate these double integrals rather than try to do this. Okay? It can be done in very simple cases. This can be done, but we're not going to do it, right? It's just too tedious. So, right? So in order to calculate these double integrals, we're going to use a property called Fubinis Theorem. And here it is. So Fubinis Theorem, we're going to let f be a continuous function over a plane region R, right? And there's two parts to this theorem, part 1 and part 2. And what I don't think they explain very well is that in part 1, we have a vertically simple region, right? So R is a vertically simple region. It's between two functions of x, g1 of x and g2 of x, right? So we did this in the last video, right? In fact, I didn't call them g1 and g2. I called them g and h, but now we're using h separately. So yeah, g1 and g2, right? So y is between g1 of x, right, and g2 of x. I can squeeze that in here, right? Yeah, so that's, yeah. So that makes it a vertically simple region using vertical rectangles, right? So in that case, part 1, oh, I moved it over, sorry. Okay, so part one just says the following, that if you want to calculate a double integral over a vertically simple region of some function f, right, you can evaluate it as an iterated integral, which is what we did in the last video, right, in the last section. And so because it's vertically simple, the iterated integral becomes dy then dx, right? Or if you prefer to use a horizontally simple region, maybe because it's simpler, right? Or maybe because when you try to evaluate the first integral, the inside integral, you can't do it, right? And then just switch the order and maybe you can. So we saw that in the last video too. So if R is a horizontally simple region, then you can calculate it again as this iterated integral. Right? Of the same function, right? You're not changing the function, but you are changing the order of integration. It's now dx dy instead of dy dx. So Fubinis theorem is essentially a way to translate this abstract double integral into one that we can actually calculate. Because in the last video, we did several examples of calculating iterated integrals. So hopefully those are not difficult at this point. Okay, so let's just get on with our first example. Evaluate this double integral, right, where f of xy is the given function y over 1 plus x squared. And R is the bounded region between y equals 0, y equals square root of x, and x equals 4. Okay, so before we do anything else, before we try to evaluate this, maybe we should graph the region. Again, in the last video, I showed you why that's very helpful. So y equals 0 is the x-axis. Y equals square root of x, we know what that looks like. And x equals, let's say, 1, 2, 3, and 4. I hope that's right. 1, and then this is 2 already, so I think I'm a little bit off here. Yep, that's 1, and then this is 2. Perfect. So here's x equals 4. Right. So I think we have our bounded region. It's this here, right? So this is what we're calling R here. So this is the region R. Right. So I'm not going to try to graph the surface sitting above it, right? I'm not going to try to draw the three-dimensional picture here. Go ahead if you want to, or better yet, use your, use that website. I forgot what it is, Monroe CC. I should post a link to that. I keep forgetting to do that. Yeah, there are applications that can graph three-dimensional objects, and go right ahead if you want to. But here we don't really need to, right? We are looking for the volume underneath this surface, right? The volume under the surface above R. Right, but above the region R. Right. Okay, so in order to calculate this double integral of this function here, well, we're going to use Fubinis theorem. Right, so now we have to decide, do we want a horizontally simple region or a vertically simple region? And I think it just comes from, do we prefer dy dx or dx dy? So if we integrate dy dx, we have to integrate y, which is just 1/2 y squared, right? And that might work. If we do dx dy, we have to integrate 1 over 1 plus x squared. Yeah, I remember what that is. I hope you do. I think it's just arctangent of x. So I think it works either way here. I think it'll work either way. So I'm going to go with the vertically simple region, right? We're going to do vertical rectangles. So this is part 1 of Fubinis theorem. Okay, so the region y goes from where to where, right? So y goes from 0 to the square root of x, and x goes from 0 to 4. Okay, you don't have to write y equals, right? In fact, the book is never going to do that. Right? If you want to know whether these are x's or y's, just look at the dy and the dx, right? If the dy comes first, then we know that, right, these are y's. These go together. And then the x goes last, then it's the outside integral for the x. Okay. But sometimes I'm going to do that just to make it a little bit clearer, if that helps. Okay, now that we've translated this to an iterated integral using Fubinis theorem, we can evaluate it, right? Let's just do the inside integral first. Remember, x is a constant here, so we can bring the 1 over 1 plus x squared outside and just integrate y with respect to y. So, yep, to be clear, right, we're just doing this inside integral here first. We'll take care of the 0 to 4 later. And the 1 over 1 plus x squared, right? So we integrate y, you get 1/2 y squared. And we're going to evaluate that between 0 and square root of x. Sorry, it's a 0 to 4. Well, the 1/2 can come outside because the 1/2 is just a constant. Is that okay? And then, when you plug in square root of x squared minus 0 squared, you just get x, right? So this is 1/2 the integral from 0 to 4 of x over 1 plus x squared. Right, so now we don't need arctangent anymore. Right, that's a Calc 2 problem. This is now just a Calc 1 problem. It's just regular substitution. Okay, so we need a 2 here. We need another 2 on the outside, or another 1/2 on the outside. And so now we get 1/4 the integral of, let's see, du over u. But now, if these are x's, u goes from 1 to 17. I hope everyone got that by now, right? I mean, right, if x is 0, then u is 1 plus 0 squared, which is 1. If x is 4, then u is going to be 1 plus 4 squared, and 1 plus 16 is 17. So that's where I got the 17 from. I hope it's not a mystery at this point. All right, so the integral of 1 over u is, natural log of u. Or absolute value. However, we're plugging in positive numbers, so we really don't need absolute value here, right? This is just 1/4 the natural log of 17 minus 1/4 times the natural log of 1. But since the natural log of 1 is 0, this is just the natural log of 17 divided by 4. That's the exact value. The approximate, is about 0.7083. Okay. So what does that number represent? Well, if we were to graph this surface, right, whatever the surface looks like, I'm sure it doesn't look like that, but whatever it looks like, right, and below it you have this purple region R, right? If we took the column above that, right, and you had this piece of the surface sitting right above it, if we want the volume of this solid region underneath, that volume will be about 0.7, right, or exactly natural log of 17 over 4. Okay, so that's the interpretation of the double integral. It is the volume of the region below the surface, but above the region R of the xy plane. Okay, so as a practical matter, that's how you evaluate double integrals. So I guess we'll do one more. Yep. Okay, so I'm hoping you can do this one. This is a pretty easy one, I think, or at least a very routine one. The region R here is just a rectangle, so I think we can draw that. X equals 1, 2, 3, y equals 1, 2. Right? So this is the rectangle R here, right? It's that region of the xy plane. And above it is this surface, z equals xy. And we're looking for the volume underneath that surface, but above the rectangle R. So how do we calculate volume? It's the double integral over the region R of this function. Right. Of course, we're given the function, right? F is just x times y. Right. And now, what's dA? Well, dA is just a tiny little rectangle here, right? And it's just a matter of, do we want dA to be dy dx? Right? So dA could be dy dx, or it could be dx dy. Right? Dy dx would be vertically simple rectangles, regions, right? And dx dy would be horizontally simple. So this is a rectangle, right? It doesn't matter. Vertically simple, horizontally simple, does not matter to me. So this could be done either way relatively easily, right? In the last example, I would, in the first example we did, I would almost encourage you to try to do it the other way. Try to switch the order of integration. I'm not sure it's, actually I take that back. I'm not sure it's doable. I'm not sure it's easy to do. So I think the order that we chose in example 1 was probably the easiest way to do it, if not the only way to do it. But in this example, you can't go wrong here, right? You just do it either way. So let's do vertically simple, dy dx. So y goes from 0 to 2, and x goes from 0 to 3. So to calculate that, we integrate with respect to y. Right? So that's going to be 1/2 y squared from 0 to 2. So we still have to plug in the 0 and the 2 here. I'm going to run out of space very soon. So we still have to do the integral from 0 to 3. But when you plug in 2 for y, remember these are y's now, you get 1/2 2 squared, which is 4, and half of 4 is 2. So you just get 2x dx, right? And when you plug in 0, you get 0. All right, so now we're down to a single integral. The integral of 2x is x squared. And you plug in 0 and 3. 3 squared is 9. 9 minus 0 is 0. So there you go. Right? The volume of that region is 9. Right? Okay? Yep. Not hard. And just to be adventurous about it, we could do it the other way. Right? We can do from 0 to 2, 0 to 3, same function, but we can do dx dy. Right? So now when we integrate with respect to x first, we get 1/2 x squared times y. But now x is going from 0 to 3, so this is going to be, let's see, the integral from 0 to 2, 1/2 of 3 squared is 9 over 2 times y. So now we have to do that, single integral, a definite integral. So when you integrate y, you get 1/2 y squared. So this is 9 over 4 times y squared, evaluated between 0 and 2. But 2 squared is 4, and 4 divided by 4 is 1, so you get essentially 36 divided by 4 which is 9. Same answer. And not that much harder to do it this way than it was to do it the other way, right? So just to be clear, the first way we did it was for a vertically simple region, right? dy dx. And then the second way we did this is for a horizontally simple region, dx dy, right? So remember, whatever comes first, that tells you whether it's vertical or horizontal. Got it? Yeah, not a hard problem. Okay, so this one's maybe a little trickier. Not much, I don't think. So we want to find the volume under the surface z is equal to e to the negative x plus y over 2. Okay, so yeah, so that's our function. Right? It's a function of either x or y, or in this case both. So negative x plus y over 2. So that's the exponent of e. Right. And what's the region? The region is quadrant 1. Right. Sorry, it should be a y. Quadrant 1. Quadrant 1 is all of this, right? Goes on forever. Right? So in other words, it's the set of points x and y in the xy plane such that x is greater than or equal to 0 and y is greater than or equal to 0. Right? There's no upper bound. Right? It goes to infinity, right? If you like, you can write it this way. That might be a little more indicative of what the limits of the integrals are going to be, right? So if we want to calculate this volume, we need to do the double integral, and we know what the function is, right? It's e to the negative x plus y over 2. Right, so to calculate this double integral, we use Fubinis Theorem. And we translate this to an iterated integral. Dy dx or dx dy. Yep, doesn't matter again. And this is an example where it doesn't matter whether you use y first and then x or x then y. So vertically simple or horizontally simple, doesn't matter. I guess, well, I'm doing y first, so I'm doing vertically simple. Okay. And these are infinite rectangles, right? They go on forever. So what are the bounds? What are the limits of integration? Well, y goes from 0 to infinity, and x goes from 0 to infinity. And you've seen these before, right? These are improper integrals. Okay. So let's see what we can do here. Can we do the first integral? If it looks a little tricky, here's my suggestion. Remember, this e to the negative x plus y over 2, you can think of it as e to the negative x over 2 plus negative y over 2. But by the rules of exponents, this is e to the negative x over 2 times e to the negative y over 2. So by breaking it apart like that, I think we're making this a little bit easier because this is not a function of y, it's a constant that can come outside. Okay. Oh, okay, so technically we don't want to do that. First of all, that should be a 2. I'm a little sloppy here. And then we're doing the integral from 0 to infinity of e to the negative y over 2 dy. Now, you saw me writing the dx over here. Don't get in the habit of that because while you could do that here, right, because we can write this function as a product of some function of x and some other function of y. When that happens, and depending on the limits of integration, you may be able to write the iterated integral as just the product of two integrals. So when that happens, and that does happen here, it makes it easier. But you can't always do that, and so don't rely on that. So just just to keep this being a pretty good habit here, let's do this integral first. Sorry, I had it in blue here before, so we'll do this integral first, and then we'll do the dx integral, and you'll see that it's not going to matter in this case. Okay, so yeah, so we still have to do this integral. We'll do that later. Remember the integral of e to the negative y over 2, right? It's e to the negative y over 2 divided by negative y over 2, right? So I think we're going to get, we multiply by negative 2, right? E to the negative y over 2. Evaluated between 0 and infinity. Hang on. I don't know why this is causing me a little bit of pause here. Because there is a substitution I'm almost forgetting about here. Right? So du is going to be negative 1/2 dy, which means when you divide by negative 1/2, you multiply by negative 2. So I think that's right. This is, yeah. Yeah, this is just e to the, yeah. E to the negative y over 2, right? Times negative 1/2 dy multiplied by negative 2. So, yeah. Okay, fair enough. But I'll leave that here if you want to figure that out, because I think that's how I got the negative 2 here. Okay, and that can come outside because it's a constant. All right, e to the negative infinity. Well, technically that's the limit, right, as say n goes to infinity of e to the negative y over 2, but that limit is 0, right? So you're going to get 0 minus e to the 0. E to the 0 is negative 1. Sorry, e to the 0 is 1, but it's 0 minus 1, right? So that means you're going to get another negative, so that'll become a positive 2 now. Okay, now we just have to do this integral. But this is the same integral, right? It's the exact same integral as the one we did just now. Right. I mean, if you're complaining, wait a minute, this was an x, not a y. Okay, change it to a y. It doesn't matter what you call it. Right? It's a dummy variable. Right? You can make it any letter you want. A w. Right? You're just going to get the same thing. Right? Which is what? Which is 2. So, right? So you get 2 times 2, which is 4. So yeah, this is an improper integral, and it's an infinite region. Right? It's an infinite region, and yet we do get a finite volume. Right? The volume was 4. So that's the that's the answer, 4. Right? So you know what's happening here, right? I'm going to try to draw the region here if I can. So here's x, here's y, and e to the negative x over y is going to be something like this. Right? It decreases very quickly. So it's a surface that's very close to the xy plane. So even though there is a finite volume over here, as x and y gets bigger, you can see that that volume gets very, very tiny. Right? So I hope that helps. Or if it doesn't, then just think of, e to the negative x. Right? If you want the definite integral of e to the negative x from 0 to infinity, I know you don't get 4, but you get some other number. I think you just get 1. Right? I think so. But that's just the area here. Right? That's just this area in here. Right? Even though it goes on forever, right, it's so tiny over here that it becomes almost negligible. Okay, there you go, right? So you can also do improper integrals, iterated integrals, just like this. Okay, we'll do another one. So here, we can express this as finding the volume underneath the surface, 1 over log y, where r is the region, it's the set of points xy, such that e to the x is less than or equal to y, and y is less than or equal to 10. And x is between 0 and log 10. Okay, so yeah, I mean, if you want to go with that order here, you don't need to graph it. This is e to the x to 10 for y, right? So dy dx. So they're giving us the vertically simple option here. And then x goes from 0 to log 10. Okay. Well, yeah, I think this option here is not so good. Trying to integrate 1 over log y is going to be a bit of a hassle because I don't know how to do that either. So I think we're going to have to switch the order to make any sense of this. So we're going to have to graph the region after all, right? So y equals, that's a weird looking y here. Y is equal to e to the x. Okay, we know what that is. Right? Y equals e to the x. Right? And y equals 10 is, well, just a horizontal line, y equals 10. Okay, and x goes from 0, so x equals 0 is again the y-axis. They like to start at the y-axis usually. And then y equals log 10. Well, guess what? That's exactly where these curves meet. How do we know that? Well, where's e to the x equal to 10? Obviously, log 10. You just solve that equation, right? So there we go. Right, so which region is it? Y goes from e to the x to 10, so it's this region here. Right. Well, again, I'm drawing it as the vertically simple region that they gave that to us. But we're going to have to translate this to a horizontally simple region this way if we have any hope to evaluate this, this iterated integral. Okay, so what are my new limits of integration here? Again, that's always the hard part. So we're switching to dx dy. Right, so x is still going from 0 to, well, we're ending on the curve y equals e to the x. But you can't do this because, right, this is, we're trying to integrate out x. So we can't have the upper limit in terms of x, right? It has to be in terms of y, right? So what is x? Well, there you go. It's natural log of y, right? Just take the inverse, right? The inverse of e to the x is natural log. Right? All right, now what's y doing? Well, y is going from not this y, not this y, and it's not the x-axis, right, because there's nothing here. What we need is the y-coordinate of this point right here. This is the smallest y value of the region. So y is equal to what here? Well, it's just the y-intercept, right? What's the y-intercept of e to the x? E to the 0 is 1. So this is y equals 1. So that's the lower boundary for y. The upper boundary how far are we going? We're going all the way up to this this horizontal line here, which is given. It's y equals 10. Okay, so now can we evaluate this iterated integral? Let's do the inside integral first. Oh, sorry, 1 to 10, not 0 to 10. Okay, well remember, log of y, right, this is the integral with respect to x, so we can take the 1 over log y outside and just integrate 1 dx, right, and that's just x. Right. Evaluated between 0 and log y, right, which is just log y minus 0. So we have 1 over the natural log of y times the natural log of y minus 0, right, over 1. Well, that's convenient, right? Log y divided by log y is 1, right? They just divide out, right? Because this ends up being natural log of y over natural log of y, which of course equals 1. So our final integral here from 1 to 10 of 1 dy, well, when you integrate that, you just get y evaluated between 1 and 10. So 10 minus 1 is 9. Sorry, that's a 0. 9. So that's the answer. So again, that's the volume under the surface. If you were to graph the surface 1 over log y, I have no idea what that looks like. Well, I have some idea because it doesn't depend on x, right? It's a cylinder. It's actually a weirdly shaped cylinder. But nonetheless, if you graphed that cylinder and you took the volume underneath this surface here, right, it would just be 9. Exactly. Okay, so yeah, this is one where they gave us the region, but if you just take their version of it, it turned out to be rather useless because this, I don't know how to integrate this. It's just, yeah, it's just impossible. Well, maybe not impossible, but I don't know the answer. And maybe you do. Maybe you're just better at, integrating than I am. But the integral of 1 over log y is not a simple integral. It's not one. It's probably not one that you did in Calc 2. Yeah. So I just typed it into Wolfram Alpha and it just spit out some name, right? The integral of 1 over log x dx is called Li for logarithmic integral, right? So that's just the name of it. So kind of useless, right? Kind of useless knowing that this is just, just the name of the function. So yeah, you're going to have, logarithmic integral of e to the x. But if we don't know how to, we don't even know what this function is, let alone how to evaluate it. So yeah, we had to switch the order of integration, right? Just like we did in the last video, we saw one like that as well. So yeah, I think that's the idea. Just evaluate double integrals by resorting to Fubinis theorem. And if you try it one way, say vertically simple, and it doesn't work out for you, then just switch the order of integration and do it the other way. In this case, using horizontally simple region. Right, so translating this to dx dy instead of dy dx. Okay, so I hope that helps, and that's the second section. And we're going to keep doing this. In the next section, we're still going to be evaluating these double integrals, but it might be more convenient to switch variables when you have, say, a circular region or a disk. Right? While it's possible to do this in rectangular coordinates, it might be easier to do this in polar coordinates. Remember, r and theta. So yep, we're going to be doing double integrals in polar coordinates in the next video.